All right, so we're going to start with X-ray creation, review that, and then we'll start talking about X-ray emission, and we'll pull up with the factors that affect X-ray emission, and then we'll finish that out whenever we get back. So, X-ray creation. We had two different ways to create X-rays. Started this on day one. So we use tungsten, and we use tungsten for a lot of different reasons, one of which is that it gives us a great big fat nucleus, right? So we've got a great big fat nucleus, and we've used the planetary analogy. You know, the bigger planets tend to draw in the space debris. You know, we call Jupiter the vacuum cleaner of the solar system. So big, has you know, it's a bigger target, but it also has a greater gravitational pull that reaches out further, so things that come through the solar system have a greater likelihood of hitting Jupiter before it gets to us. So, and we've got some other big planets too that also absorb some of those things. But we use that in this analogy because what we said early in the semester is that even though I draw this real big up here, how big is the nucleus of even a tungsten atom? I've never seen one, right? I've seen a collection of them. I passed it around, right? But as far as seeing a tungsten atom, no, can't. So what we're doing, and if you think back to the atomic numbers of the subatomic particles, a proton, the atomic number was 1, right? So what was the atomic number of an electron? 0, right. So even though we've got 74 protons and however many neutrons, we still have something that's very, very small. So each individual atom in that is so small that you can't see it. And we're going to shoot at it something that's so small that it almost doesn't exist. We don't give it a mass, right? So the likelihood of getting close to it is pretty slim, right? Why don't we get hit with more meteors and stuff? How big is the universe and how big is the Earth, right? We've got a lot of big stuff floating around out there, but we're a small target in a great big expanse, right? And that's kind of what we have here. So the likelihood of us lining up electrons, and I'm just going to kind of make them like this. I know that looks like an auto transformer. I just don't want to draw a bunch of circles. All right, so we line up all these electrons, and we're going to give a more you know, realistic idea of what the nucleus of a tungsten atom is going to look like. All of these electrons, I shoot at that thing. Any of them going to get close to it? In a word, yeah, yes. Some are going to get close to it. Are many going to get close to it? Answer is no. Answer is no. So, if we're shooting all these things at this tiny little bitty speck, most of them are going to pass so far away that the gravitational pull of that speck is not going to be all that great. Okay, so what is it that causes us to have high energy brems? Why does the electron come in and make a very sharp turn? It's a gravitational pull, right? So what affects gravity? Gravity, kind of like magnetism. Where is it strongest? Close to it, right? So of all these, if only a few of them are going to get close to it, what does that mean? Most of our X-rays are just going to go into heat, or most of our electrons are just going to go into heat, right? And the ones that do create X-rays are going to be high energy or low energy? They're going to be very low energy, right? So we're going to take a look at that here in a bit, but most of them are going to be low energy. So again, we talked about X-rays being inefficient. X-ray creation being inefficient. And we did this little exercise once before. An amp is 6.3 times 10 to the 8. Is either 17th or 18th power. It doesn't matter. You don't have to know how many electrons are in an amp, but that's how many electrons are in an amp. okay? So to write that out, what we've got is 6, 3, that's 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. I think I counted those out right. So how many electrons is that?
A lot.
A lot. It's a lot, right. So our brems, you know, most of these electrons are going to come in, they're going to pass so far away from the nucleus of the atom they don't amount to anything, except for adding heat, depositing the heat on the anode. So it's just heat. Some of them will diverge just a little bit, so they're traveling in like that, and they just barely take off in a different direction. We get an X-ray photon out of that. So let's say we set 100 kVp, and the energy of the X-ray photon is determined by the difference. What's the difference? Subtraction. The subtraction, right? So the difference between incoming and outgoing electron energy. So let's say it came in with 100 and it leaves with 99. Did we get an X-ray photon? Yeah. And what's the energy of it? 1 kVp, right? So what we say is that the electrons, you know, they travel across the tube. Most of them just complete the circuit, don't create X-rays. And depending on the kVp level that we're using, we say maybe, you know, 99% creates heat. So 99%, or saying it the other way, only 1% of all of those on 1 amp exposure would become X-rays. Okay, do you use, you know, what would a 1 amp exposure be for 1 second? What do you use? What do you set? Milliamps, right? So with milliamps, how many milliamps are there in an amp? 1,000, right? So when's the last time you made 1,000 mass exposure? I hope you haven't. All right, so let's say we set a 1 mass exposure, okay? So that's 1/1000th of an amp, right? So 1 mass exposure, we knock 3 zeros off. Now if we say that 99% of these electrons we send across the tube become X-rays, that means only 1%, or 99% become heat, that means 1% becomes X-rays. So we knock off 2 more. Okay, but that's just the X-rays. Let's say 99% of those are these things. We knock off 2 more. How many X-rays do we create off of 1 mass exposure? In a word, a lot, right? So it's just a numbers game, right? We use a lot of electrons to give us still a lot of X-ray photons, even though they're, you know, a whole lot less than the number of electrons we use. So, brems. The things to remember about brems. All right, so we've got electron in. Electron doesn't interact with anything except for the nuclear force, the nuclear, you know, the nuclear pull. It slows down. The electron slows down, and as it slows down, it gives off its energy in the form of X-ray photon. So the closer we get to the nucleus of the atom, the more likely we're going to be able to get an X-ray photon worth using. All right, so let's say this one came in with 100 kVp. It leaves with 1 kVp worth of energy. It's going to kick off an X-ray photon, and that X-ray photon is going to be 99 kVp. Right? So again, brems reacts with the nuclear field. The electron changes direction, emits a photon that's equivalent to the difference between the incoming and the outgoing electron energy. It's brems. Statistically, you know, the book says that 85% of your X-ray creation is due to brems. I don't know how they figured that out. maybe they, kind of dissected the X-ray beam and figured out exactly how many 69.5 kVp X-ray photons that we created that would be your characteristic, and estimated how many should have been created. I don't know. I don't know how they came up with it. Maybe it was a wild guess. I don't know. To me, it's a wild guess because we've got 85% undergoing brems. This is what they're telling us. Okay, and with brems, we're shooting something that's so small at something that is so small it almost doesn't exist, at something that's so small we can't see it. Right? So that's brems. Now we got to draw a bigger atom, because we've got to have electrons. The other is characteristic. All right, so the gravitational pull of the nucleus, tungsten nucleus, on the electrons in the various shells is going to be unique to the tungsten atom. Okay, so no other atom is going to have exactly the same pull, especially in a K shell, as what tungsten has. It's unique to tungsten. All right, so let's say you share characteristics with, I just gave it away. Okay. The reason we call it characteristic is because it's characteristic of the tungsten atom. Okay? You switch atoms, that gravitational pull, that binding energy is going to be different and specific to that atom. So for the tungsten atom, this thing is held into place with 69.5 keV worth of energy. On a one-for-one basis, 69.5 keV has the same energy as 69.5 kVp. So a couple of things here. So we send these electrons across, and now, we're shooting. We're trying to get some brems, and with brems, we're shooting something so small it doesn't exist, almost doesn't exist. It's something that's so small we can't see it, right? But now what we're going to try to do is we're going to try to hit some of these electrons. So what am I shooting? Something so small it almost doesn't exist, at something that's so small it almost doesn't exist, right? On top of that, it's moving. Okay, so it's rotating around the nucleus. So, it's for that reason I have a hard time buying that 15% of our X-ray beam comes from this, right? Maybe it does. Again, people a lot smarter than me work on this, but so what you need to lock in, though, is according to the textbook, this constitutes 15% of our X-ray beam. So if we send an electron and it interacts with that one, and let's say, the kVp and keV are kind of two sides of the same coin, equal energies. Let's say we set our control panel at 60. What's going to happen? It's going to go doink. And now we just got, this poor free-floating electron. But is it going to dislodge this one? Will that overcome this? Answer, no. Okay, so what we know about our characteristic creation is we have to have at least this energy or higher. So if I bump this up to 70, will I? Yeah. Now, how many X-ray photons are we going to get at 70 kVp from characteristic? Probably not a whole lot. Not a whole lot. So if I bump it up to 100 kVp, might I have more characteristic than what I had at 70? Answer is yeah. Yeah. So we're going to take a look at that on Wednesday, whenever we come back to it. Okay. So the brems spectrum and the introduction into brems spectrum, and if you can understand the brems spectrum and how we're going to manipulate it on Wednesday when we come back, then radiographic technique gets easier, okay? So if we were to plot X-ray creation on XY graph, and we were to say that this line represents our mass, electrons we send, and this represented the KVP, the energy level of the resulting X-ray photons, then what we would have is if we increased our mass, then we would get an increase in numbers up this way, right? Let's not go with mass. We'll go with, I just want to not conflate mass with the number of X-rays that we create at this point. Okay, so number of X-rays we create. All right, so, and the reason for that is because we're going to talk about mass and numbers on Wednesday. So just think numbers and don't equate it to mass. So at the face of the target, we just looked at it. What are most of the X-rays that we're going to create? High energy or low energy?
Low energy.
Low energy, right. So most of them, most of the X-rays we create are going to fall closer to this axis right here. So if I set 100 kVp, what does the P stand for? Potential. It's peak. It's the peak energy, right? So it's the highest energy that you're going to make once you set those dials. So if you set 100 kVp, that X-ray photon comes in and loses 100% of its energy in a single shot. That's only going to happen by brems. Then what we're going to create is 100 kVp X-ray photon. But we're shooting tiny things at tiny things. So how many of those do you think we're going to get? Very few, right? So we've established that you're going to create a lot of low energy X-ray photons because you're shooting tiny things at tiny things. We're going to create very few high energy X-ray photons. So what our creation spectrum would look like then is this. This would represent, in this example, 100 kVp. Peak energy, almost none. Minimum energy, this is 0 down here. We're going to create a lot of them. Okay, but this is where you're inside the X-ray tube, right? It hadn't even gotten to the glass. You're inside the X-ray tube. This is the face of the target. That's what it looks like. But you got X-ray tube, right? You got anode, and you've got cathode, right? The X-rays are created right there. What's it going to hit before it exits the protective housing? Not the oil yet. Oil's not inside of there. What's the first thing it's going to hit? Well, it hit the target already. The electron traveled across, hit the target, hit the glass. All right. So what's the word? Not radio parent. It's radiolucent, right? So it's going to, the definition of radiolucency is selective absorption of low energy X-ray photons. So is the glass going to absorb some of these down here? Yeah, absolutely, absolutely. So then it's going to absorb all of the 0 energy, but not many very much higher than that. But what did I lose? Low energy. I lost numbers. Okay, I lost a few numbers. Are they numbers that mattered? No. So what's the next thing the X-ray beam is going to hit? Now we're getting into oil, right? So, oil radiolucent? What's the definition of radiolucency? Selective absorption. How do we know oil is radiolucent?
You don't see it on image.
No, you don't see it on image. But what are you made out of? Especially after you hit your freshman 15. The fat is just solidified oil, y'all. Yeah, I'm just crushing morale right now, right? So do X-rays go through you? Yeah, absolutely do. So are they going to go through that? Do you absorb X-rays? Even in your softer spots? Yes. Is that going to absorb? Also yes. All right, so now what it's going to do is it's going to take away some of these low energy X-ray photons, and now we have no, 1 kVp X-ray photon. and our brems spectrum looks like that. Okay, so you're noticing two things. One is the very highest point of this thing right here is coming down, and it's also going that way, right? We're losing some of, so you notice three things. We're losing some of these over here, okay? So then what's it gotta go? Something has to hold the oil in, right? So what's it gonna go through now? The housing, specifically we call that the window, right? So it's gonna go through the window. The window's probably also gonna be glass. So we already established glass is gonna absorb some x-rays. So it's gonna knock it down a little bit more. What happens with tube age? We get tanning, so older tubes, I can knock this down a little bit further. So what does it gotta go through now before it gets to the patient? Light bulb over here, something to reflect the light bulb. Yeah, mirror. What's on the back side of the mirror?
Lead.
Probably silver. I guess they probably could use lead, but it's probably silver. But some sort of metallic stuff, and the purpose for the light is to reflect, or the mirror is to reflect light from here, so that we get an accurate radiation field, a radiation field that's accurately reflected by the light field. Okay, so we've been going through this in sophomore year. We'll go back through imaging in this semester in your sophomore year. So I don't know if I mentioned this to them. I know I mentioned it to them, but I don't know if I mentioned it to you or not. So the collimator, the thing about the collimator, the mirror and the collimator housing is the mirror has to be mounted at a specific angle, and that's 45 degrees. The reason it's got to be at 45 degrees is because the stream of electrons, if it was at any other angulation, the stream of electrons would still be coming, or stream of photons rather, would still be coming straight down, but the light would be reflected somewhere else. It's got to be a perfect 45-degree angle. So what might cause that angle to fail? Well, you know, you bang it around a tube, so be careful with the tube. Also, because light and x-rays behave the same way and they diverge, the distance between the light and the mirror, and this is never drawn to scale, the distance between the light and the mirror has to be identical to the distance between the mirror and the focus. Okay, so it's got to be really, really precise to accurately reflect radiation field. Okay, so again, we've got glass, but we've got glass with what on it? Some sort of metal. We've well established by this point that metal absorbs a lot of x-rays. It's a thin layer of metal, so it's not going to, you know, totally block the x-rays, but it's going to take a chunk out of this, right? So now our brems spectrum, as it emits from the x-ray tube, looks a little like that. Okay? There are a couple of things that bear explanation. So you set a technique, and this is going to represent the number of photons that you create. Okay, and again, in this example, I didn't want you to equate that with mass, because we're going to take a look at what happens as we increase or decrease mass, what happens to this thing. So the parts of the brems spectrum, we got this toe out here that represents the highest energy that you can create. We've got the very highest point right here, which should represent the average energy that we create. Okay, so as you know, whenever we had the X-ray beam at the target, we had much more lower energy X-ray photons. So what happens to our average as we increase filtration? If the height of this thing represents our average, right, and we got rid of all those low energy X-ray photons, what happened to our average? The average gets higher. Okay, okay. The average beam energy. Okay, so I didn't really make myself completely clear. The average X-ray photon energy, even to dial it in a little bit tighter. Okay, so the average X-ray photon energy increases with increased increased filtration. Okay, we're going to draw that out again on Wednesday. So the height of the bubble comes down. The height of the bubble represents numbers, right? The peak of the bubble represents average, right? So this end represents the highest energy, this end represents lowest energy, but there's something missing. How else do we create X-rays? Characteristic, exactly. So if we have a brems spectrum, let's say you see a brems spectrum drawn, and you're not given any information on it, what could you tell me about that brems spectrum if you didn't know anything else about it? Okay. What could you tell me about the difference between that brems spectrum? Peak energy kind of did a hoop-de-doo. And that one, what's missing?
Second bar.
Yeah, a little spike right there, right? What does that spike represent? Characteristic, right? So again, I ask, what can you tell me about this one? Knowing what you know about characteristic X-ray creation. Bingo, bingo. This X-ray beam had to be above 69.5 kVp. And looking at that by quite a bit, right? This one? Below, yeah, didn't make the cut. Okay. Okay. So we're going to talk about that. You know, we really just kind of covered two of them. Filtration. Filtration lowers the height of the bubble, pushes it towards a high energy side, and you know, lower KVP. That's one of the things that the results that we get with decreased KVP is that we lose our characteristic spectrum. Okay. So again, we're going to dissect this on Wednesday. We're going to leave it there for right now. And so let me kind of show you what I've been talking about, the difference between 8 and 9. Okay, so we're going to talk about the brems spectrum, everything that affects the brems spectrum. So what you see on page 136 is target material in the brems spectrum. On 137, the chart on the left is mass in brems spectrum. Chart on the right is KVP in brems spectrum. And on page 138, that is filtration in the brems spectrum. So then if you flip over to chapter 9, what does it say? What's the title of chapter 9? What did we just talk about?
Emission.
Emission, right. So, you know, chapter 8 and chapter 9, you know, in my opinion, I think they should kind of be shuffled in together. I didn't write the book. I'm not selling the book, so, you know, it's none of my real business. It's just that I feel like chapter 9 is just a review and a repeat of chapter 8. So we should be able to finish up on Wednesday. Any questions? Okay. Destiny, is it okay if I say Happy Thanksgiving now?
Yeah.
Okay. Happy Thanksgiving, everybody.
Me too.